this problem we have an alpha particle, we'll call that QA, sitting at the origin, x equals 0, and it's fixed. And then we have a proton here, which I'll call QB. So QA has a charge of plus 2e, which would be 3.2. And then QB has a charge of just plus e. Alright. And this is at x is equal to 5 nanometers, so pretty close. Alright, the proton is allowed to move freely, and it's clearly going to move this way, and it's going to reach an x coordinate out here of 25 nanometers. Alright, and the proton is initially at rest, and we want to know what's it going to be the final velocity when it gets out there to x equals 25 nanometers. Okay, so, well, you gotta, this is a non-uniform field problem, right? Because the field due to charge QA is radial and it diminishes with distance. So the force on QB right here is going to be pretty strong, but by the time it's out here, the force is going to be pretty weak. So that means we can't use Newton's laws. We can't say the sum of all forces equals ma, because the acceleration and the force is not constant. So this is a work energy problem. We say the sum of the works done by all the forces is equal to the change in kinetic energy, and the only force we have to worry about in this problem is the work done by the electric force. Now, the work done by the electric force can be calculated a few different ways. The first method we have is that you take the force times the distance times cosine theta, and of course that doesn't work here because the force isn't constant. This formula only works when the force and the angle between the force and the displacement vector is constant. Our second method is minus the change in potential energy, which I think we're going to use here. So I have minus the change in electric potential energy is equal to delta K. Now from our formula sheet, we have that minus the change in potential energy is minus our moving charge multiplied by the potential of the charge that the charge is immersed in, right? So charge B is immersed in the potential from charge A. So let's calculate the initial potential due to charge A. That's going to be K QA over Ri. Okay, so here's our Coulomb constant, and then QA, and then we divide by 5 nanometers. Oops, just 10 to the minus 9. And that's 0.576 volts. And then our final potential, VF, is going to be KQA over RF. Which is, RF is 25 times 10 to the minus 9. So we basically are just going to take this first answer and divide by 5. Okay, so now we pretty much know everything. So minus QB delta VA is 1/2 mv squared minus 1/2 mv naught squared. So this term is 0 because it starts at rest. And I get minus 1.6. Okay, there's QB, and then VA. That's going to be VF minus VI. That's going to equal the change in kinetic energy. That's going to equal the final kinetic energy. Now, the mass of a proton you can look up on your formula sheet is 1.67 times 10 to the minus 27 kilograms. Okay, so that gives me V squared is 8.83 times 10 to the 7th. It's positive, right? Notice that this is negative, but the potential that it moves through, VF minus VI, is negative, right? As usual with a positive charge following an electric field line, it moves from a high potential down to a low potential, right? VF and VI. Right, notice that I'm putting hats on all my V's here to keep them separate from V naught, from our velocity. which is a good habit to get into. Alright, so anyway, when I solve this, it's 9,400 meters per second.